Hello everybody. Let us look into introduction to quantum mechanics. We know that the kinetic energy of a particle is given by half mv square, where v is the velocity vector and m is the mass of the particle or the body in motion. Now squaring the velocity, because velocity is a vector quantity, so squaring velocity means the dot product between the two vectors, so will give me the squared magnitude of velocity. So if v is expressed in 3D vector, it will have three components vx, vy, vz. If we take the dot product of the two vector quantities, we will get it equal to vx square plus vy square plus vz square. That means it is the magnitude squared velocity quantity. And we also know that the velocity is equal to the time derivative of the position. This is an important point to be understood because the two quantities, one is position and the other is momentum. We have to understand properly because these are the two quantities which are important in quantum computing instead of the velocity vector, because in Newtonian and Lagrangian mechanics we prefer to deal in v, but in Hamiltonian mechanics we prefer to deal in momentum. So Hamiltonian mechanics is the concept of mechanics which actually lead to quantum computing. So therefore we are we need to be familiar with the position and the momentum terms more as compared to the velocity term. So therefore that's why what we are trying to do is we are trying to put this kinetic energy equation in terms of momentum, not in terms of velocity. So we know that momentum is given by mass into velocity, so just by making certain adjustment we can find out the kinetic energy to be equal to p square by 2m. Just an observation here, because when the kinetic energy is expressed in terms of the velocity, the mass comes in the numerator, whereas if the kinetic energy is expressed in terms of momentum, mass comes in the denominator. So this is just an observation I am making here. Now there is one very important quantity that has to be understood, and its quantization actually leads to the name the quantum computing derives. It's the quantization of the angular momentum that gets the quantum computing gets its name. So angular momentum quantization in Bohr's model. In Bohr's model, the electron orbits around the nucleus like a planet orbits around the sun. Now, in Bohr's model, the electron behaves like a planet orbiting the sun so that it has circular orbits around the nucleus, as I was just mentioning here. Electron has a fixed tangential velocity, so electron will have a, I will come to this point just a little bit further, just in little bit because when a little bit after, just a bit afterwards, yeah, it's here only. But so what I mean to say is that the electron will have a tangential velocity and fixed radius, so therefore it will have fixed energy. So electron has fixed angular momentum, right, because it has got fixed tangential velocity and fixed radius if it is orbiting around the nucleus in a circular orbit. Now another because if you see the diagram here, nucleus is there, so electron is moving around the nucleus in a wavy squiggly line. So this squiggly line basically shows that the electron behaves as a wave. So another important property that electron can have is the electron can behave as a wave. So it has wavelength. That is why a squiggly line is there in the diagram to depict the wave character. Now the bold line here, there are two lines that make a circular orbit. One is the bold line. The bold line represents the circular orbit. The wavy line represents the standing wave pattern that the electron will create to explain the wave nature. Now if the electron is behaving like a wave, so it will have a certain wavelength. That means we can generate a condition that relates the radius to the wavelength. Now the circumference of the circular orbit is given by 2 pi r. So that means the standing wave pattern traverses 2 pi radians and comes back to the same point. It means that wavelength has to be multiplied by an integer to get the circumference. So if there is because of the wave nature, there will be wavelength. So since the electron is completing the orbit in a wavy kind of path, so therefore this circumference will be equal to n times the wavelength, right? So where n is the integer. Now if we know that the wavelength is given by h over p, that is due to Broglie's expression. Now that means h over mv, if you replace p with mv, you will get lambda equal to h over mv. Just replace this lambda value here, that means replace lambda with h over mv. So what you will get is 2 pi r equal to n into h over mv. So just get this equation mv, just get this quantity mvr on the left hand side. To the right hand side we will be left with nh over 2 pi. So this mvr is basically the angular momentum. This is equal to n, which is an integer multiple, right? And h over 2 pi we can replace with h cross. This is reduced Planck's constant. This is again a constant. So I can express the angular momentum to be n into h cross. So therefore, now h cross is constant, and angular momentum is related to integer. That means the angular momentum comes in discrete chunk. The values of the angular momentum will be in discrete chunks, and L is also the cross product of the R and the R and P. That comes from the MVR formula only. So therefore, what is the condition that explains the discrete nature of the angular momentum? This is the condition: 2 pi r equal to n lambda. What does this equation say us? This from the Bohr's model, it says that the electron orbits around the nucleus, right? So that means it is covering a circle. So circle will have the circumference 2 pi r, and the wave nature of the electron. So if it is making waves also, that means how many waves it will make around the circle covering one circumference will be equal to n into lambda. So 2 pi r, so these two quantities have to be equal, 2 pi r equal to n lambda. Now this is the basic condition that leads to angular momentum being discretized or quantized. Now as I was just trying to explain, the electron will have a tangential velocity v. It will have a centripetal force acting on the electron that keeps the electron moving in the circular orbit. Now this is our nucleus. Nucleus will have a charge plus Ze. So plus charge, plus is there because of the protons. Z is the atomic number, E is the charge on the proton, and R is the radius. Now to keep the electron moving in the circle. So therefore the centripetal force have to be equal to the electrostatic force acting on the electron. Now what is the electrostatic force? The electrostatic force is given by this is general expression of the Coulomb's force, K into Q1 Q2 by R square. Now what is Q1? Q1 is the charge on the nucleus, that is plus Ze, and Q2 is the charge on the electron. So another E will come here, so that will make the Coulomb's force, and this is our centripetal force. These two have to be equal so that the electron remains orbiting around the nucleus. So from here we can find out V square. Now from here we can find out V square, and we also know that the so one V square comes from the equality of the centripetal force and the electrostatic force. We also know that the angular momentum is equal to n h cross. So just replace L with mvr and find out V square from here. So you have V square coming from two sides. One is the angular momentum side, the other is the equality of the two forces. So just equate these V square terms. So you will get left hand side you will get n square h cross square m square by r square, and right hand side you will get this term. From here you can calculate the value of the radius. So this is your radius. Now all the quantities like k, z, e, m, h cross, they are all constants. So therefore the radius is equal to r1 n square. So what is r1? R1 we are substituting for h cross square, all the constant terms. So therefore the radius r1 is the radius of the first the lowest energy level. So therefore Rn is proportional to n square. That means the number of the orbit. Now the total energy of the electron is given by the kinetic energy plus the potential energy. So kinetic energy is half mv square, we know. Potential energy will be kz e square by r. Now please remember that in the potential energy term you will not get r square here. That is for the force. So only r will come for the potential energy. So that's what I have written down here. So total energy is kz e square by 2r minus kz e square by r. Negative sign is because of the electron potential of the electron. So total energy comes out to be equal to minus kz e square over 2r. Now we know that the nth energy level is given by the, we just derived it here. If you we can use this expression of Rn equal to R1 into n square. So that will give me, because this is my En. So En I can replace, this is my Rn basically. I'm not putting n here. This is in general Rn term. Rn will be equal to R1 into n square. So that means my energy will be equal to the energy of the first orbit divided by n square. So that means energy is inversely proportional to this n. Now from here, so n is the index. What does n say? N actually tells us about the number of the energy level. That means there will be many energy states like first, second, third, fourth, fifth energy state. So n will give us that number, whether it belongs to the first energy state, second energy state, and so on. E1 of course is the fundamental energy. That means the energy of the lowest level, lowest energy electron can have. Now there is an important formula we have to look for, that is the Rydberg's formula. The job of Bohr's model is to explain the emission and absorption spectra of the atoms. Now if you see, if you have higher energy state and electron jumps from the higher energy state to the lower energy state, it will emit an electron. The energy of the electron will be equal to delta E, which is the difference between EI and EF. So delta E is equal to EI minus EF. So if EI minus EF is greater than 0, that means energy is being emitted. If EI is less than EF, that means EI, this difference is less than 0, that means the energy is being absorbed here. Now, so because of this jump of the electron from the higher energy state to the lower energy state, a photon will be emitted. Energy of the photon will be equal to delta E, and it is given by h nu. This is from the photoelectric effect. Now nu we can replace with c by lambda, and if we just and this is equal to EI minus EF, right? And we also know that the energy, EI energy is equal to E1, that means the first energy level divided by I square. I am using the formula of E1 upon n square. Now I'm in place of n, I am using I index here, and here I am using F index here. So therefore the overall expression becomes as 1 over lambda is equal to minus E1 over hc, 1 over f square minus 1 over I square. This is known as the Rydberg's formula, where n is the principal quantum number. Now this is the Rydberg formula, and this describes the spectral lines of hydrogen and forms the basis for understanding the Rydberg states. Right. Now these those with very, now what are Rydberg states? With large values of n. That means very large values of n actually tell us the Rydberg states. Maybe n may range from 50 to 100. Now what happens when uh, when in Rydberg quantum computing, so when atoms are excited to higher principal quantum number, that means if they are taken to the Rydberg state, so what happens is the neighboring electrons will also be excited, right? So because of very large dipole moments. Now one of the electron you have taken to the Rydberg state, now the neighboring electrons will also get excited. Now when you see, a Rydberg state is a very high principal quantum number, n, right? The electron sits far from the nucleus in that case. Now giving the atom a giant electric dipole polarizability with the neighboring electrons. Now if two nearby Rydberg atoms interact extremely strongly actually. Now if you try to excite multiple atoms with a resonant laser, the first atom that reaches the Rydberg state shifts the Rydberg level of the neighboring electrons also. But now if you are trying to, if that shift exceeds the laser bandwidth, the neighbors are off resonance and cannot be excited. So one atom blocks the other because it will need more energy, right? So when you are trying to excite one atom and you are trying to take it to the Rydberg state, because of the interaction with the other atom, the energy levels will be increased. Now it will need more energy to, if you are trying to take it to the Rydberg state, but that will not be possible because it needs more energy levels to be excited to the even more higher energy levels. In that case, a kind of Rydberg blockade is created. So long range dipole dipole interactions is the reason for this Rydberg blockade. Now strong controllable interactions ideal for implementing multiple gates. So, and see, this is the key mechanism for quantum logic, because when one atom is excited to the Rydberg state, it shifts the energy levels of nearby atoms due to strong dipole dipole interaction. Now this prevents other nearby atoms from being excited. This is known as the Rydberg blockade. This blockade creates an effective two-level system over multiple atoms. Now, this blockade is actually responsible for the entanglement and the controlled quantum gates, right? And this is just the definition. In the end, I'm just giving the definition of reduced Planck's constant. Thank you.